Hello, welcome to the third day of the conference here. My name is Philip Müller, and I'm talking today about the gaming console, Orange Pi Neo, which is based on Linux. So let's go back to history lane. The first gaming console, which is not by Nintendo, was the Aoyai. So it came out 2013. And it had Android on it. So it was the first console where people had the opportunity to work and do their own games. But it failed. So they had only 2,000 units sold and only 1,250 games supported. In 2020, someone said, hey, why not put Linux on it? Because it's a dead hardware. So yeah. The next was by Valve, the Steam machines. So what they had, also Linux. They had around 500,000 sold, but the games were less, only 1,000. So Valve had to rethink. And a couple years later, the Steam Deck came out. So 2021, they had a lot of games, still 1,000 in the beginning, but the form factor was different. And so far, they sold around 3 million units. After that, 2023, the Steam Deck OLED came out. And what changed? Well, the first batch was sold out, so it was a hit for them. And the games are now at 13,981 games, which you can play on this mobile device. So we come along in 2024 with the Orange Pi Neo. We are intending to do the initial batch of 50K, and then on demand we produce more. And we have around 14,000 games which you can play on this device. So how we port Linux to it? Yeah, there is always the question, which came first? The hen, the egg, or the chicken? So to do that, we have to port Linux to the device, of course. Then if the device is not produced yet, we need another device to replace that. So I was looking to something, and you need developers which are doing the same goals. So what was on the market? On the electronic shelves, there was this Asus ROG Ally. So when I was back in Munich, Germany, I went to the nearest media market and bought that device to start porting my operating system, which is Manjaro. So what was the hardware of this device? So it's similar to my device. It has the AMD Ryzen Z1 Extreme, the same graphics card, a similar screen, 16 GB RAM, 512 watt hard drive, and Dolby Atmos. So there were a lot of problems which will come with this hardware design. Then we have Windows 11, my Asus, and a lot of drivers for Windows. So what didn't work? Part of the controllers works, but not every button. So this was a problem. Then graphic works, that's great. Screen works. What didn't work was sound. So you couldn't play any games with sound. So this was a challenge. We had to support the gyro. We had to support also the sound card and some buttons, of course. And Windows. If you have Windows, you have updates. So if you start the Asus Ally, first was you greeted with a Windows setup. You have to create an online account. You have to do updates. And then you have updates of the drivers and updates of the launcher. So you stand there, you want to play a game, and it took you about 1.5 hours to start the game because you only have to download the game. So yeah. And if you look here at two different models, what's the difference? The UI. Every manufacturer changes the UI, so you don't have the same user interface. And how we change that? Well, we put Linux on it. So we have Manjaro, we have KD Plasma as the UI for the desktop. We have some parts of Chimero OS, which is a gaming operating system, and a bunch of other things, including Steam, ButterFS, and other launchers. And with this, we can start and have the same UI as we want to have it. So the first, what we have to do, testing on the device. Is your operating system working? The second is give the vendor the feedback, what they have to change, and also do testing and feedback with the vendor, so everything is working. What worked? So on my device worked part of the controllers, which is good. Graphics works, screen worked, audio worked. So we had one more point which is actually working than on the Asus Ally. And the touchpads worked as well. So we only had to work on suspend, the 4 buttons which were not working by the default drivers, and the gyro. So how we did that? We did first the basic functionality, so the operating system worked. Then we fixed the issues in firmware and hardware. So it was a lot of devices coming to my desk and I have to change, hey, this button didn't work. You have to change that in the firmware. And the last thing was we have to polish the experience. So this is what we're doing now. What is important? Well, the power management, of course, you want to have a long battery life. The cooling is also something which you have to work on. RGB, some people like RGB to have some fancy coloring around. The controller, there are a lot of input devices. X input is the standard, which everybody wants to use, so we aim for that. The gyro was also something which people like to use, so you can turn the device upside down and the game will react, or you have a flight simulator, you can do some turns. And what also is clear, the build quality. You want to have a good device, so all the buttons should be working and so on. And you have to stay curious to adopt changes. So this is mainly what you do for porting the device. So are there any questions regarding the device itself? I have here the device. You want to test it? You want to test it? Okay. Yeah. So no questions regarding how to port.
Good morning, everyone. Good morning, sir. I have a question for you that are these software available for any other Linux distribution or just Manjaro?
So the device will start shipping with Manjaro, but we have all the drivers there. So you can port your Linux system to it if you want to. But if you get it from the manufacturer, it has Manjaro, but we open source everything. So you can port to different operating systems as well. So it's like more or less the drivers are there and we did the heavy work so others can adopt, and maybe that will bring a lot of people to use it.
Do we have root access to that? Lock it?
Yes, you have root access. Yeah, you can fully change everything. Yeah.
What made you choose AMD platform rather than another platform, say ARM, as an example?
AMD was already established, so you can simply port everything The Steam OS is based on AMD hardware, and therefore it's easy to port. It's just a new hardware, faster CPU, and therefore the work is less. If you look for Intel, there is the MSI Claw, and they have a little hard work because the graphics card is new. So if you have a game, it doesn't start. You have to emulate it to say, hey, this is an AMD graphics card, then it starts. So there are a lot of things, and we want to have the first product easy. So that's why we are using AMD. Any more questions? Five minutes. Huh? Well, we try to do the sales hopefully in May or June, depending on the manufacturing. So first we have 300 units for reviewers and testing out the build quality. And after that, we will have mass production to 50K. And if that works great, we will ramp it up to about 50 more or 200 more, depending on the demand. So it's like, if people want to buy it, then we say to the factory, do more devices. So the factory can produce about 30 units in a week. But if we need more, then we can employ more in the factory to make that faster. You have a question? No.
So did you do like a licensing agreement together with Steam, Valve?
Well, I'm working with Valve. Valve wants to open up the SteamOS for other vendors. So I'm in talk with them. And the first thing what we initiated was the legal issues. So if you have the first user setup on Steam Deck, you have the easy way to set it up. So if you start my device, it is set up in 2 minutes instead of the 120 minutes in Windows. So you simply boot it up, log in your Wi-Fi, your credentials, and then you're in and can enjoy the game. And for that, we have to clarify the legal issues with Valve, which we are currently talking, but also they want to open up the devices for others. So the SteamOS might have in future also different devices, yeah. Okay, then that was all from my side. And you can look around. I'm here in the convention and you can try out the device.
Okay, so I guess it's 8:45. Welcome to my talk. I'm Piotr Król, and I would like to introduce you to Dasharo, open source firmware distribution. So I'm founder of 3MDEP, Poland-based consulting company, which specializes in embedded firmware. So mostly open source BIOS, but also embedded Linux. I'm also instructor in open security training, which are some fancy free stuff, which I will advertise at the end. So maybe first, like short exercise. How many of you know this logo? Raise your hand. Whoa, almost no one. So there are 2 people knowing what's coreboot. So coreboot is open source firmware alternative to BIOS. And maybe you don't know, but every Chromebook's running coreboot. So this is the BIOS for every Chromebook. So maybe it would be easier with this one. How many of you know this logo? Ever seen this logo? Also, not many. So, there are a little bit more. So this is UEFI. UEFI UEFI Forum is an organization which defines specification for interaction between BIOS and operating system. And based on this specification, there is implementation maintained by organization on GitHub, which is called Tayano Core, and they do reference implementation of BIOS. So there is like huge C code base, which you can use to develop BIOS for your computer, for your device. So I guess it would be harder further because those are even more niche projects. This is, who knows this logo? No one. So this is Linux boot. So this is very interesting project, open source firmware project, where Ron Minich, creator of coreboot, decided to put a Linux inside the SPI chipset of the computer. So you don't use, when you're putting a power on your device, there is no BIOS, or there is little bit of BIOS, but then immediately Linux kernel starts. So why he did that? Because he assumed there is no need to write the drivers twice. Typically on the system, one set of drivers is in BIOS and then of course another in your operating system. So he said, like, why I should write drivers twice? I will reuse Linux kernel drivers in BIOS for initialization of the system. And last logo is maybe very niche project, but very interesting. It's very security focused. It's Handhelds. So this is like a coreboot downstream distribution, very specific, using hardcore cryptography, GPG, USB token for checking integrity of the firmware. So I really encourage you to Google for coreboot Handhelds, and you will find GitHub repository, and you can read about this really secure secure firmware distribution. So what I will talk about is Dasharo. Dasharo is another downstream distribution of coreboot made by 3MDEP, by my company. And the goal of Dasharo is to provide open development, firmware resilience, platform security focused distribution with UEFI interface. So any modern operating system can boot based on that. So how the status of the project look like and what kind of impact Dasharo already made? So first of all, so we already merged to coreboot upstream like 16,000 lines of code. This is maybe not much, but another 20,000 is in progress. And we also got a power port, which is like 50,000 lines of code, which also will need a merge. So, so in case of hardware compatibility, it's also like we beginning. We have 17 platforms supported right now. There are 5 another which are in progress. We already released like over 500 releases. We run over 40,000 tests on those releases. All the tests are published. All the source code is published, so you can build those images, you can flash those. But we also provide the binaries, which you can immediately use on supported platforms. In case of market share of the devices, we support IBM Power 9, especially the Raptor Computing Talos platform. We did quite a lot of Intel, but the most of stuff we did is for AMD, especially for firewalls from Switzerland, from a company called PC Engines. In case of community, we have a community of over 250 people. There is around the communication channel is on Matrix. There is around 2,000 messages a month, so not much. But if you are interested, you can join and see how this move on. We were highlighted by news release in various places. So Tom's Hardware wrote about us when we did the port for MSI Z690. There are a bunch of other medias. Phoronix likes us very much. So Phoronix is like a open source news media outlet. So they like what we're doing very much. So there is a lot of stuff. PC Gamer wrote about us. So you can see that this is not only some unknown niche project, but there is some impact and we are growing. I wanted to show you a comparison between various distributions. I guess the most important are two last lines. So maybe let's go through columns first. The rows are the various open source firmware, you can say, distributions. or not open source firmware, because the row here is like closed source, BIOS vendor, proprietary stuff. Yeah. So maybe let's start with the first column. It's about openness. So the question is if the source code for my BIOS is open, and you can see that typically your source code for your BIOS on your computer is not open, and you typically don't know exactly what you're dealing with. There may be malicious code there may be malware, there may be bugs which are not fixed. There may be like outdated microcode, which cause that you are vulnerable to various meltdown spectra like bugs. But anyway, so that's what's different for the typical vendor BIOS. Then the question is, if you in given projects you can get binaries, or this is just source code and you have to compile yourself and you have to deal with the toolchain problems and all the technical difficulties which are related to building something. Yeah. So in most cases you get the binaries. The difference is with the coreboot. Coreboot is just it's like Linux. Like Linux provide source code. It does not provide binaries. Distributions provide binaries. Yeah. So yeah. So the point here is that the coreboot does not provide binaries. You have to compile it yourself. You have to decide what options you're choosing while compiling. The next thing is public long-term support. So the question is if the platforms which were enabled in this project will be supported for long term, or they will be dropped. So most of the distributions have long-term support because they support like even over 10 years old hardware. But in case of coreboot, they have policy that if there is old platform which cause problems for further development, they just make a branch and just move on, like remove that platform from the head of tree in their repository. This happened multiple times. And of course, like in case of vendor BIOS, you never know. Typically, consumer hardware got like maybe 2 years updates of BIOS, maybe 3 years. The server hardware from serious companies may get like way longer support, but that's it. Maybe industrial embedded stuff may get longer support, but typically you're not getting long support for BIOS from BIOS vendor. In case of commercial support, some may need commercial support for the BIOS. So Heads got it. LibreBoot, I didn't find the information on the website, but I guess if you will call them, then probably they will provide. In case of coreboot, there's dedicated website where you're going to coreboot.org and you have like consulting, you're going there are a list of companies which will support you. In case of vendor BIOS, it depends, but mostly yes, you will get commercial support. But the point is, if you are a small vendor or individual, like unlikely. You have to be reasonably big to get that support. And with Dasharo, you're getting the support. In case of public community size, definitely Heads and LibreBoot, which are maybe not so well known here, already have quite established community, which is reasonably big. Coreboot has huge community in comparison to Heads, LibreBoot, or Dasharo. Vendor BIOS, like you can go to forums of various vendors, but there is like some small group, like I don't know, 50 people who are interested in the BIOS modifications or doing something with BIOS. So yeah, so typically it is small and do not last long. And Dasharo is growing, so I would say it's between the vendor BIOS and the Heads. Going further, transparent validation. So the question is, what was validated? So sometimes you're getting BIOS update and there was very descriptive release notes. Performance improvements, bug fixes, something like that, which is like not saying anything. So with Dasharo, you're getting transparent validation. So you exactly get information. This test was executed with this procedure, and the result is that. If there is a bug, there is a link to bug on GitHub, and everything is transparent and open, and you can check it. With Heads and LibreBoot, they have a small testing community. This is not backed by big organizations. So that means they typically rely on, like if bug pop up, there is GitHub issue and they discussing there. There is no formal testing and there is no transparent validation like a list, what was validated on given release. With coreboot, there are no binary release, so there is nothing to validate. And with vendor BIOS, sometimes there are some tests, especially there are hardware compatibility lists published, but you don't know really what they validate, what operating systems they validated, which version, which service pack, and so on and so on. With Dasharo, you get that. In case of validation scope, how big is this test scope? How many tests they running? Yeah. I guess like with heads, like very minimal, the heads running themselves. There is CI which do the builds. Then with LibreBoot, I guess there is a little bit less. With coreboot, there is just building. There is CI which do the just builds, nothing else. So if not building, they consider this is broken. If building, they not test anything else. Yeah. With vendor BIOS, they validate a lot. They have huge labs. They have a lot of various hardware, and they can really do a lot of validation, but they do not provide the results of that validation. So that's the problem. And with Dasharo, we have like quite a lot of tests. For some platforms, we have even 500 tests, and we're still growing. In case of NDA docs, so non-disclosure agreement documentation, which means access to the silicon vendor documentation, which give you ability to fix potential problems with BIOS or report problems related to hardware. So yeah, so typically for heads, developers do not get that because they don't sign, and LibreBoot, they don't sign NDA. Coreboot, some developers are working for corporations, so they have access. Of course, vendor BIOS have access, 3MDEP and Dasharo got access. In case of size of public documentation, like most of the projects got very little, UEFI vendors, proprietary vendors got very little documentation. You can go to docs.dasharo.com and see how much documentation we have. We have like tremendous big documentation, a lot of information you can find there. So that's the comparison. So I wanted to pitch you quickly about something which is called Dasharo Trust Root. So essentially, there is a mechanism of making the platform booting only the firmware that you want. So sign it by you. And that's typically what Lenovo or any HP, Dell, any OEM doing. They create blow a fuses in the processor with the public key, so no other firmware can be booted, only theirs. Yeah. So we have also this possibility for those who want it. Those fuses are here in some silicon vendor technology deep inside the silicon. That means typically that those fuses are used by something what is called management engine or platform security processor on the AMD. It could be BMC on server platforms. It could be boot ROM on ARM platforms. And then from that, the root of trust starts of the platform, and the boot process continue. It can continue through various means, through firmware, which could be Dasharo, coreboot, Diano Core, I don't know, U-boot, trusted firmware, and then of course pass the control to the operating system. This is logo of Zarhus, the other project that we're doing. And of course, in operating system, you're doing what you want with your technology, with C, Rust, Go, whatever. Okay, so you may ask, okay, this is all open source, and so how you earn money, yeah? So what's your business model? So the business model is like quite complex, like on this diagram, but essentially for Dasharo, there are three main streams. The entry subscription, so this is subscription-based model. Someone can pay us to get the binaries to their email. Of course, the code is open, so they can compile themselves. So it's up to them if this is waste of their time or this is like okay for them. Someone can buy support package or there are dedicated products which going to customers. Okay, I get information that I should end. So let me give you this slide. If you want to buy Dasharo, those are links. Slides will be published by the organizers. This is my contact. If you want to talk with me, please free to reach me out. And I wanted to give you some free stuff. So this is free stuff. So with Zino Kovács, former Apple security engineer who was responsible for secure boot of MacBook Pro M1, he created this portal for free education, free security education. So if you go to POST2 FYI, you will get free trainings. And various of them are very low level. So this is x86 architecture, coreboot, UEFI, debuggers. So you can learn a lot from that for free and then get a job. And if you want to work for us, feel free to send CV to us. There is a website dedicated, 3mdev.com/careers. You can check what kind of position we have open, and that would be it from my side. Thank you very much. Do we have time for questions? No. Okay, so if you want to talk with me, please catch me in the lobby, and I will be okay to answer any questions. Thank you. Bye-bye.
Hello. Hello, everyone. So welcome to my session. So today I'm going to talk about our work in ARM processor. So welcome to the world of ARM. So, as a key feature of the ARM ARC64 processors, they support multiple cores. At this moment, we are still leading in this industry. The average in the server area domain, there are usually 64 or 128 cores in a single silicon chip. So that's an advantage for ARM processors. So we have more computing unit. And at the same time, vendors are trying to add more hardware accelerators into the same chipset to accelerate specific tasks. So there is a point. So we need to we need to balance between our jobs between the cores, CPU cores, and the specific hardware accelerators. So today I'm going to talk about the work we did so far in this area. So, so people come to say the longer your subject, and then the less attention you get. So I tried hardly to make a shorter one. So I'm going to touch SVE, so which is the ARM vector solution in the server domain, and the hardware accelerators in my session today. So that's a brief introduction of myself. I come from Linaro. Linaro is an organization. We worked on the ARM software ecosystem. So today's content, as I mentioned, we touched a little bit about the software solutions and the hardware accelerator solutions and the work we did in openSSL and JDK. So in this session, if you get to learn something about SVE or hardware accelerators or openSSL, okay, I will feel better if that can help you. So why crypto is important? So first thing is, so we get more and more data in the modern days. So, and the second thing is the government, there are a lot of regulations, rules, laws enforced by the government all over the world. I just checked that in Vietnam, we have the government has such laws, and also China, also US, both the government and the industry-wide. So they enforce us to apply encryption on our data. So that's big stuff. So for thinking about every text files, every byte we store in our server, in our disk, you need to do some encryption. And when you want to fetch it, you need to do decryption. So that's a lot of work. The same thing goes for the storage space. We need to compress things. We need to decompress. So to conquer this need, we have two methods, as I mentioned. So we have the CPU processor core method, and we have the specialized hardware method. So, yeah. So let's first check the ARM solutions. So in the software solution, for that, most of the time we are talking about the instructions. So in the ARM world, we have specialized features, specialized instructions, like for SM4, like for AES. So you can find specialized assembly instructions in the ARM ISA, so to processing such type of job. So people are working on that to use the assembly specialized instruction to optimize their libraries. For example, the erasure code or the SM4 encryption library in the openSSL. So another software solution is to use the vector instructions, like a simple single instruction, multiple data. So we have AVX solutions in the x86 world, and in ARM we have SVE. So SVE stands for Scalable Vector Extension. I will mention it later. So also ARM introduced the matrix extension recently, which is specifically useful for the AI processing. So what is SVE? So SVE is vector processing is scalable. That means the register size can be defined by the vendors. So each chipset vendor can pick their proper size for a vector length. You know, they can choose from 128 to up to 2048 bit vector length. So and the beautiful thing for SVE is, so as a programmer, software programmer, when you write your code, you don't need to care much about the actual vector length. So either it's 128 bit or it's 512 bits long. So they provide the instruction mechanism to support this, to cover this for you. So in FE, that's a bit about too much detail. So it has 32 registers, vector registers. As I mentioned, the vector length can vary from 128-bit to 2000 bits maximum. And as we provide the P register, predicate registers. Predicate registers is like a mask. So, we, in the vector processing, we define the data as a lens. So the predicate register works like a mask. So you provide the P register, you provide the mask, and then you issue the instruction. So only the lane mark has a proper mark, either 1 or 0. Here is 1. So have a proper mask will be executed. So you don't need to move or cover the this lane somewhere else. You just keep it here, but put a 0 mask in the predicate register, then issue the command, then you get everything done for you. So there is another example, like it's a multiply and plus instruction. So here we can see that we with this mask, the lane 0, 1, 2 will be processed. With 0, 3 is masked. It goes unchanged. So that's quite makes things simpler for programmers. So another important feature for SV is it's vector length agnostic. That means you, especially in a while loop, you don't need to know the specific architecture chip you are running. Your software has a 128-bit vector length or 256-bit vector length. You just use it's implied by the instruction. For example, here you have the INC instruction. So traditionally in Neon or some other architectures, you have to know that when you increase the index, the vector length is 16. That means 16 byte, right? You process in one loop, you only process 16 byte. So, but in SV world, so whatever, it's if you are running in a 128-bit machine, it increase 16 byte. If you are running on a machine with a 256-bit vector length, then it will mean you increase the index by 32, right? When you write down your program, you don't need to care about the actual vector length. That's what it means. Okay, so beyond that, ARM released, really? Okay, I go quick. So ARM extends the SVE to more domain, SVE2, and also the matrix solutions. Okay, with matrix solutions, they introduced the bigger file, register file, so you can process the do some complex stuff like the outer product or to vector. Okay, so now let's go to the hardware accelerator. So hardware accelerators is another solution. We know that sometimes CPU frequency, their capability goes to a limit. So there is chance that we use specific hardware to do specific computations. Like in Kunpeng 920 chipset, that's the chipset manufactured by the HiSilicon. So inside this chip, there are 4 accelerators working on compression, security, and something more. So we are going to explain the security part. It can do the AES, encryption decryption. It can accelerate SM4 encryption decryption as well. So to support that, Linaro worked with HiSilicon, developed the UADK framework. So this is a software framework, but it works for the purpose of this software is to support the hardware accelerators. So it is constructed based on the SMU technology. With SMU, you get the same virtual address between the device and your program, your code. So you just need to give the virtual address to the device, and then it will find it through SMU. Your device can find the proper physical address. Okay. There will be another session today in this room from my colleague. So if you want to learn more details about UADK and the underlying technology, you can come to join his session. So, okay, we mentioned software acceleration, we mentioned hardware acceleration. So now, how can we get the most efficiency, most capability out of it? So that means we need to find some balance. Okay, so we build some balancing strategy. We consider some how and in which conditions we put the jobs to which processor, being the software accelerator or the hardware accelerator. We consider the CPU, we consider the memory bandwidths. So when we define the strategy, we need to consider all these criteria. Here in Linaro, we define this solution. It's based on the OpenSSL 3.0. So there are pretty new features comes with the OpenSSL. So OpenSSL 3.0 was released last year, and yeah, the older version, previous version OpenSSL 1 is obsolete so far right now. So the new features here is each application can define their own context. Within the context, it can load their own provider. Provider means execution unit, like an implementation. So you can register different multiple implementations to the same library context. And it also provides a method store. So when the user application want to fetch, that means want to find some processing unit, implementation unit, it needs to fetch from the method store first. So that's something new. So based on that, you will know that we do the balance by implementing a load balancing provider. That's a special provider. So your application just need to register with this single provider register. And then you load the other providers into your application's context. And then in the load balancing provider, get the mirror of the real provider. Okay. The real provider. So in your application, it's about here. It's called combine the load balancing provider, and this provider will have the information of all the other providers you registered, you loaded. Okay, so with the strategy which is implemented by the load balancing provider, your application can go among all the child providers. So to find the best candidate for their for their job. Okay. So then we implemented we use the Java. You know, most of the applications in the big data world right now is in the written by Java. So there are Hadoop, HBase, and much more. So we need to export this capability, the load balancing capability, to the Java world. So our method is to implement another. They also call it provider in the Java world. Sorry about that. So people like this name, I guess. So the KE provider will in the Java, it will call the load balancing provider, and then load balancing provider will help the application to allocate to assign the tasks to either the hardware provider or the software provider. It's also easy for to use. You just need to change one line in your JDK. Xiong JDK is the version derived from the openJDK project, and it's open sourced by HiSilicon, Huawei. Okay. So here are some. Sorry about that. Okay. I just need 2 more minutes. Okay. Thank you. And here are some measurements. So we see with the load balancing feature at the same CPU utilization, like the red one, we get higher bandwidths. So similarly, here, same CPU utilization, we get higher. And here is to get the same bandwidth we use with the balancing. We just need lower CPU utilization. So here is another demo we did on the HDFS Hadoop file system. So with our method, we can achieve about 30% performance gains. So with jobs assigned to both the hardware accelerator and the CPU software core. Software accelerator. Okay, yeah. For open source software, we always welcomes your contributions. Here's our project. This project is incubating under the openEuler Big Data SIG. So welcome to log in, join the community to check the code, to find the way to utilize your hardware better. So again, I'm from Linaro. Okay, that's almost it. Linaro works on ARM software. Yeah, welcome to ping us. Yeah, for any service request. Thank you.
Xin chào. Morning, everyone. My name's Andrew Wafaa, and I'll be talking about how you can get benefits of working on ARM and help with your ARM hacking. So, quick overview of who I am. As I said, Andrew Wafaa. I head up ARM's open source program office. I look after our upstream interactions, community engagements, such like. I also wear many hats, as you can see here. I'm on the UXL Foundation. So Guodong was talking about accelerators. That's all about accelerators. Sit in the Zen project for hypervisor. I'm on the steering committee at Linaro and FreeBSD Foundation, as well as chairman of the Octo project. And I also am the chairman of Open UK. So, how many people know about ARM? Does anyone? No? So we've got a couple. Cool. So just in case you don't know who ARM is, we're a semiconductor design company. We don't make anything. We come up with IP and ideas, and we get paid for those ideas, which is brilliant. But our technology and our designs have been in over 270 billion devices now. There's over 36, about 33 billion that have been shipped to date this year. Yeah, there's over 15 million people developing on ARM in one shape or another. So ARM in Vietnam, at the end of last year, our education and university team hosted a delegation from the Vietnamese education organization, and pleased to say that we have signed an agreement with the Vietnamese government to join the Semiconductor Education Alliance. What does that mean? It means we're building the future on ARM in Vietnam. And so we're very pleased to see that hopefully in the very near future, the curriculum for computer science and other things will be based on ARM, or at least have ARM included. So first stop when you want to start developing on ARM, whether it be from a hardware or software perspective, is our developer hub. That is, we've spent a lot of time and effort redesigning how we can actually get information into the hands of developers. And so we've created the hub here to help collate all of that. It's very simple. It's, what's the area that you want to develop on? You go there. You've got videos from ARM experts, both internal and external. You can find out where next ARM-based event is, etc. And there's also some training things, training modules available. Some of that is free. As part of the developer hub, if you want to work out, okay, I want to develop on X, how do I do that? Does that software work? We've just launched our ecosystem dashboard, which you can get to from the developer hub there. And that actually lists all various softwares, what the earliest version that supports ARM is, what's the status. There's commercial products, there's open source products, so you can actually find out early on as to how much work are you going to have to do to actually get something working. As part of that, we also have our developer program. We strongly encourage you to participate in the developer program. It's relatively lightweight. It is a program based around Discord server where we have staff from ARM, we have staff from our partners, we have ambassadors, and we have regular, everyday developers out there, all participating, and there are a number of meetups and such like there. And get on board. You can get some nice swag and other bits, but it's a great place to actually find other people that are working on the ARM platforms. You want to say you're working on Kubernetes. What's the best platform to use for Kubernetes? You can find out there. What are the various quirks or differences that may arise? You'll find out very easily, and you can have a nice social conversation with somebody and actually build a community around what you're trying to do. Pretty sure somebody's tried it, so learn from them, and that'll help you move forward. As part of the developer program, we've created something called Learning Paths, where it's a GitHub-based web content. So we've got, as you can see, a number of topics, and you're actually able to edit and provide pull requests if you find a mistake or issues. If you've got questions, it feeds back into the developer program. And so you can actually learn, you can contribute if you found a way of doing something that is not listed there. You can create a learning path, you can submit that, and that helps the whole community ultimately at the end of the day. So we've recently released a new product called Performance Studio. One of the complaints that we've heard from developers, both large scale companies and individuals, was there's no real tooling to analyze performance of your software stack. How can we make sure that, you know, we can get the claims that ARM is making on how good our hardware is, right? And so Performance Studio came out. It's a suite of tools, effectively, where you've got targeting CPUs and GPUs. It's primarily designed for application developers, not low-level hardware developers or firmware developers. And it's free, completely free. We're not going to ask you for any money. You can download it from the Developer Hub. So it may seem familiar if you install it, because it is. We used our mobile studio as the basis for it. For those that don't know, ARM's primary market segment has been mobile for quite some time. Over 90% of phones run our designs, and same with tablets. And so we had a tool set for that segment, and we've expanded that. We've added Frame Advisor for more graphics aspects, and then as well as RenderDoc. And we've ensured that it's not just focused on the likes of Android, but general purpose Linux as well. So workflow is a fairly standard performance analysis workflow of monitoring your work load, see what's happening, getting the reports of what's actually happening, what's failing, what's not meeting what the triggers that you thought you needed, that then allows you to ultimately optimize that workload. So as part of Performance Studio, we've got Streamline. And as part of the Streamline suite, there's the Performance Advisor. So help with profiling for, or automating your profiling, should I say. And then the reports that get generated are designed for monitoring what you're doing. And then you can actually quickly and easily digest what's coming out of those reports, so you can respond quicker to that. We've also got the sampling profiler piece to the Streamline toolset. See what's happening with the CPU, see what's happening with the GPU, and see how they're both interacting. If you've got workload that's moving from one to the other, or having to call on one of the other processing units, you can see that in real time. Relatively low overhead for both your CPU and your GPU. With any profiling, there is going to be some form of overhead, but we've kept this to a minimum. And so with that, you can actually see clearly what's going on, when, what's triggering things, and just help move things along. So Frame Advisor is the new addition, and this is focused primarily on the graphics side. There are more and more platforms coming out based on ARM with multiple types of GPUs now. So my machine here is Lenovo X13S. It's an ARM-based platform running Qualcomm chipset. There's some new platforms coming out from Lenovo, Dell, and HP. And there's going to be more different chipsets there. Qualcomm, there's MediaTek, there's talk of NVIDIA, there's talk of a number of others. So hopefully that market will change. Microsoft also have their own Surface Pro platform. Yeah, so this way you can actually see what's going on. Performance Studio is a relatively, or should I say, Frame Advisor is a relatively new component. And so we are keen to hear back from users as to what's working, what's not working, what's missing, what would you like to see, how do you use things, etc. So please email us at performancestudio@arm.com. We'd be super keen to get your feedback. As part of that, we've added RenderDoc. RenderDoc is widely used within the industry from a graphics debugger perspective. It's got full Vulkan support now. We've ensured that it works well on ARM and targets our GPUs as well. We're trying to be good citizens with upstream. There are going to be times when upstream RenderDoc can't accept some of our changes for either licensing issues or whatever else, or they just don't want to because it's too specific to a particular problem and it's not in the maintainer's roadmap. And so that's, we will be pushing as much as we can upstream. There will be some things that will have to remain downstream, but it's all going to be accessible through Performance Studio. And again, Performance Studio is free. We're not charging anything for that. And Mali is ARM's family of GPUs. And so we've got the offline compiler there, providing shader, syntax, and performance aspects. So just to reiterate, you can get Performance Studio from developer.arm.com, and we'd love to hear feedback on how you're finding it, etc. So drop Performance Studio at arm.com, an email. So I think I may have tried to recoup some time a little bit too quickly there. So any questions? Yes.
Thank you. So it is very interesting that from ARM people come here and talk about ARM. ARM is the most used processor in the world, right? So, but there are RISC-V. So I want your opinion, or maybe your future statement or anything from ARM regarding RISC-V. I mean, RISC-V is open source, and the speed, and how about in the future? What do you think?
So future with RISC-V, I'm not sure how much I can say officially, but I think as we've seen, if we look back and learn from history, as an example, there's going to be space for a number of architectures. It depends on how successful they are, etc. One of the crucial pieces that I think ARM benefits from is an expansive software ecosystem. We've spent a lot of time, money, and effort and manpower on ensuring that the ecosystem is where it needs to be, and we're continuing to work on the software ecosystem. You can have an open piece of hardware, but if you don't have software, all what silicon is expensive sand, right? So you need a solid software story for your hardware. Conversely, without hardware, software is just an empty idea, right? You're not going to see anything. So there is a symbiotic relationship, but you need that software to make that hardware work. And I think ARM is in the lead in that respect. We've spent a lot of time, money, and effort, and we're continuing to, and we're expanding our investment, working with our partners, customers, and the wider developer community. Possibly. Having an open instruction set is one thing. Controlling that instruction set to ensure that it doesn't fragment, that's a different story. And I think it is a significant risk, no pun intended, that having an open instruction set allows people to diverge from what the central idea is. And so when it comes to actually supporting the software, it might run on a particular platform, but because there's so many different implementations, it's not necessarily going to be able to run well ever, because you will need to have, and it might be okay from a community perspective, but if you want traction with commercial vendors, for instance, the cloud vendors or major ISVs, etc., they hate change. They hate choice, in so much as they want to be able to write their software for one architecture, one platform, and they will tune that and harden that to the ends of the earth. But it's very limited. So if you go and look at, I don't know, for instance, SAP as an example, and you want to deploy SAP on hardware, you will find that the list of platforms that you can deploy it on is very small, because they have to concentrate on, tuning, security hardening, etc. And when you diverge from a hardware perspective, it makes it much harder for those software vendors to be able to get the most out of that hardware. So there are always going to be certain use cases where one architecture is going to be better suited than another architecture. What we are doing is providing choice to the ecosystem. With regards to x86 versus ARM, it's, whilst raw compute power may be better, if you look at the power per watt and power per single thread performance, then you'll see difference. But x86 does have slightly better multi-threading. We are closing that gap rapidly, but from a power per watt perspective, we're far more powerful for using a fraction of the energy. And moving forward, that is one of the big issues. The age of AI that we are in now, the power consumption for training all this data is just going through the roof. It's ridiculous. People like OpenAI, etc., they need power stations, not data centers, to be able to power all the training that they're doing. And so I think the focus is going to change from raw power. We want it as fast as possible, we want to be as economical as possible, because it's going to cost not just the environment, it's going to cost the companies big dollars in, you know, paying for the power and cooling, etc., and of all the hardware. I think from a application perspective, so as you said with databases, etc., there are some databases that will, for the most part, always work okay on one architecture or another, but they will operate very well on some architectures. That's always going to be the case. I think NoSQL databases may operate better on ARM versus a traditional RDBMS, but yeah. Keep watching. Keep watching is all what I say. I can't say one way or another. We're always looking at advancing compute, and you know, traditionally ARM has always been in the shadows. We've been quiet. You know, we don't have a jingle or whatever with the advertisements or whatnot yet. We'll see what happens. But we are trying to make sure that people are aware that we are here for the long run, and we're investing heavily within the software community at large. ARM GPU? No. You can use this for the CPU as well. Possibly that there are GPUs is heavily driver driven. And so if we can access the driver code, then yes. There is perf-based, yeah. Thanks very much.
And Xiong, technical research from K Laboratory for Embedded and Network Computer of Hunan Province, Hunan University. I'm here to share the event on behalf of the openEuler community. And my topic is Zephyr, Zephyr-Based virtual machine. And let me have a brief introduction of myself. I'm a PhD student from Hunan University, and in the open source community work and openEuler Zephyr maintainer and president of the open source student association at Hunan universities. At the same time, I'm Zephyr project and openEuler Zephyr developer. And I'm here to share the Zephyr and what's Zephyr? Zephyr is open source embedded hypervisor based on the Zephyr tools. You may heard of the Zephyr tools. It's a popular open source embedded operation system in the Linux Foundation. And the Zephyr is developed based on such excellent open source embedded operation systems. And why we talking about Zephyr? The first is the demand for virtualization in embedded scenario is increasing. Example, intelligent transportation systems maybe should use a hypervisor to run multiple OS in one platform. And the second, there is a relative few hypervisors based on the real-time hypervisor. So it's maybe meaningful for someone to use it. And then for the student or the developer, they may need to learn the hypervisor to know how it works. The Zephyr may be a simple sample to help them to understand how to design a simple hypervisor and how to use the simple hypervisor. And then we will talk about how to deploy the Zephyr. Now we can deploy the Zephyr on the virtual platform or a real hardware platform. Example for ARM fixed virtual platform on the QEMU emulator. It's a virtual platform, and then we can deploy it on the developer board, like Rock chip RK3568 system chip. And if you are new to the Zven, I recommend that you use the QEMU emulator because it's more simple than the others. The Zven is maintaining the compatibility with the Zephyr origin build systems. It means that you can use the REST command to build the Zven just like build a Zephyr. And then you can use the QEMU emulator to start the Zven. This is the start command. Maybe use the QEMU Arch64 emulator to start up Zven. And finally, you can get a QEMU Zven example. For example, Zven host shell, and you can use this shell to create or to run in the virtual machine. And that is what to deployment the Zven. And you may ask why we use the Zven. In some embedded systems, it's needed to meet the practical deployment requirements of rich features OS and time constraints. For example, the intelligent control system in the car or intelligent industrial control system. And in such a system, they may need two types of OS. One is the rich feature OS for in the car. Just like in the car, we can see it's an intelligent cockpit with the data visualization and the human machine interactions. And with another type is the real-time OS for intelligent driving, just like the charging control, power control, and other motor control. And these two of them can be considered as a twin starter coexistent systems, just like the figures. And the rich feature OS is as the main star, and the real-time OS is as the second star. Just give a example, like the main star may be openEuler, and the second star may be a QX for QX Atos. So in such a mixed character system, they a single hardware platform, and with multiple OS, multiple VMs, and with various applications for different functions. That is why we to develop such a embedded hypervisor. And then we introduce the framework, the Zven. We can see in the picture that Zven can divide it into 4 layers, include the hardware layers, hypervisor layers, guest OS layers, and applications. First of all, hardware layers, we support the MVA architecture CPU, including support the core device such as process, memory, and interrupt controller, and etc. For the virtualization layer, it's about the core virtualization extension models like the vCPU, vMemory, and vDevice. And for the volatile framework or other shared memory or other function. And Zven reuse the Zephyr kernel wise, just like this, and reuse this Java's models and other function. And then in the guest kernel layers, it's we can use the Zven to create multiple virtual machine like the Zephyr Atos or openEuler or other Linux with ARM8 architectures. And the up layer is the application layers. We can run the real-time or no real-time applications for the different function. And then we talk about the Zven in openEuler embedded. You can see in this picture that the openEuler embedded will need embedded virtualization to boot several OS. And Zven will as a part of an open embedded ecosystems to provide some virtualization capability for to run multiple OS. The main function of the VM including the managing the virtualization resource. For example, managing the process resource or memory resource or the device resource. And then it can providing the API to the upper layer VM, just like to apply to provide hardware access API for the service VM to control the real hardware. And then it's supporting multiple operating systems, including the openEuler, embedded Ubuntu, and the Zephyr-Based. And in the future, we are support the Android and FreeRTOS. And it is the VM in the openEuler embedded ecosystems. And in the future, we will try our best to merge the VM to the Zephyr mainstream, to merge into the Zephyr ecosystems to be a international community with a part of as a part of the Zephyr-Based. And then we choose the features of VM, the technical features of VM. First is the system configurability. It supports flexible configuration of the VM, can switch it between type 1 to type 2 hypervisor as needed. The second is the dynamic resource. It includes the dynamic memory allocation, dynamic device allocation when VM starts, and the adaptive task scheduling. And the third is the device virtualization. It includes the device pass-through and the device for virtualization and the parallel virtualizations with the volatile framework. And the fourth is the inter-VM communications. We support communication between VMs based on the Wafaa framework and the shared memory. And the fifth is the real-time features. We reduce the real-time performance of the Zephyr-Based and to support some preemptive or deadline scheduling strategy. And the sixth is the edge-side inference. It's about support for Padlet, edge-side AI inference framework support like models like RISC-V and others. And then we just tell the detail of the technique of the GVM. First is system configurations. It's about the how we to configure the over GVM. It's include two parts. First one is how to configure the VMs, and we use the device tree to individually to configure VM according to the description. Device tree description file, just like this, and we use this so we can decide how many devices the VM can get and how many models they can get, or can patch some system info to the VM. And the second part is the kconfig systems, just like the Linux, and we can use the kconfig system to compare the VM itself. For example, to decide which system will be built into the VM, and what's the VM function or other models can be built into the VM. And with these features, VM can switch from the type 1 and the type 2 hypervisor. For example, if it's the type 1 hypervisor, it means that a few of the subsystem may be built into the VM itself, and if it's the type 2 hypervisor, it means that the most of the kernel device or other device may be built into over VM. And the second is the dynamic resource management. It can provide the flexible use of hardware resource. It also can divide to two parts. The first one is the device allocations. It means that VM can unify all the devices in the hardware board and to assign the device to the specific VM when the VM starts up. And then is the memory allocations. VM use a double linked list maintain memory space for each VM. And VM will build the memory build the page table for each event to translate the VM's virtual address to the physical address. And then we also even also can provide different page table to different OS. Maybe a small page table for Zephyr VM or a bigger page table for Linux VM. And based on the Zephyr Hyper Memory Management, even you support the quick rapidly memory allocations. It makes the VM more easy to use. And then the device virtualizations. Even use different virtualization method for the different device type. For example, for the core device, just like the interrupter controller or clock controller or the PCIe bus controllers, we use the full virtualization method. Because if the improper access to such a core device may cause fatal error in the system. And then we support the parity virtualization device, just like a volatile block based on the volatile framework. And it's common in other virtualization systems, just like Linux KVM or Zen. And with the volatile framework, we can easily to add a volatile device to our system. And then is passed through device mode. It's based on the Zephyr's device mode. And with this device mode, we can initiate the device and lock the device to the idle device list when the system boots. And then when we want to start a VM, we will to instantiate the virtual device and to use the virtual device drive to allocate the virtual device to the VM. And when the VM want to access the device, the VM will establish a MML map for each VM, so it can directly access the hardware and do not need to Cynic or other mechanism. And then for the interrupter management, even handle the device interrupt through the driver's API and can redirect the device interrupt to the VM. And the first is inter-VM communications. It's with the VM communications, it can enhance resource sharing and collaboration between virtual machines. Just like the VM with Zephyr and the VM with the openEuler can communication with others. And with the Avishman standard framework, we can implement the data sharing between the two VMs based on a shared memory, just like the memory load. And this memory load is to organize into a AVI tree for a quick search. And then this framework is highly portable and it's suitable for multiple operating systems. Now it can be deployed in the Zephyr and the openEuler, and we can easily port it to the Ubuntu or other operating systems. And finally, with such a shared memory method, it supports real-time high-speed communication between VMs. And then is the real-time features. Real-time and even have a real-time assurance based on a Zephyr RTOS platform. You can see that it supports different scheduling queues like a single list linked list or a double linked list or read block trees. And it's also supports multiple scheduling strategy like collaborative or preemptive priority and earliest deadline first real-time scheduling. And because our design is a lightweight kernel, so it has facility to real-time performance analysis or verifications. And the final is the edge-side interface. Zven is support real-time inference on the edge side under the virtualization environment. It's because the Padlet and the TensorFlow Lite are supported on the Zephyr-RTOS VM. So when Zven to boot Zephyr, it can to run a Padlet and the TensorFlow Lite. And this it can meet the real-time requirement in the source-constrained embedded platform. And with such embedded hybrids. With these features, it can expand the application domain of the Zephyr and make the Zephyr and VM more opportunity in the edge side, and it make the ecosystem more better. And this is our use case of Zven, and it's a self-balanced car. And in this board, it's running two types of OS. One is the openEuler, and the other is the Zephyr-RTOS. And the hardware is 4-links OK3568C developer board. It's based on the Rock chip RK3568 system chip. And the software is just described and is one Zven and one Zephyr and with one Linux. And the Zephyr is real-time control. It can achieve process control of self-balance, and it can be seen as the demo of a simple mixed corrective system. And finally is our open source works. First is the Zven. Zven is a project on the openEuler source communities, and you can, if you want to try Zven, you can go to this link and to try to download the code to try the Zven. The second is we are sharing our Zven video in the Zephyr Developer Summit as a global embedded open source summit in 2023, and we make Zven is competition project in computer system developer capacity competition in China, and finally a part of Zven is merged into the Padlet Pad community project. And that's all. Thanks, everyone. And also thanks to the opportunity provided by the openEuler and FOSSASIA. Yes.
I'm not really familiar with Zephyr, but I am interested to know whether the Zephyr bigger machine can be used for higher or bigger machines like AMD Net 64.
No.
Let me repeat also. Interesting to understand to know whether Zephyr machine can be used for bigger machine.
No, it's just in the embedded system. No.
Cannot be used for bigger machine.
And yes, it cannot use in a bigger machine. It cannot.
Why
Yes,
cannot?
because
x86.
because it's a different architecture from the ARM v8, and if you want to use it in the Intel, we should to port it on it, and this work and we don't have to do it.
Zephyr machine only for ARM.
Yes, only for ARM. Yes.
But the Zephyr OS.
Okay, just make a Zephyr is a small OS, and it supports multi-architecture like ARM64, x86, RISC-V, a lot of architecture, but it's mainly for embedded scenarios. for example, automotives, robots, industrial controllers. So I mean, for other scenarios like server, like cloud, it's recommended to use KVM in Linux. There are already a lot of solutions in in the IT scenario, right? But is mainly aiming for embedded systems, right? Yeah.
So the goal is to create as many as possible OS for the system. So before it, switch, So I tend to use the more smaller OS than bigger and heavier OS like Handhelds.
Yeah. It's not. We design it is not to to replace the role of Linux plus KVM. Yeah. So. What's the difference? Because Zephyr has ability of real time, safety, security. Because if you want to pass some certification, for example, in some area like automotives, it requires. All the software must be pass the certification. It must be safe. Okay, Linux cannot pass the certification because Linux is too large, it's too complicated, right? So. Yeah. So if you want to use, so if you want to use, aerospace, automotive, Linux, cannot be the, the root of, real time or root of, safety or security. Just like our cell phone, your face, your finger, data is not stored in Android or iOS. There is a security island, which is controlled by a small OS like Zephyr. So, yeah.
So my question is, you can use Zephyr as the FOS on the bigger machine for hypervisor. You say hypervisor, right?
Yeah. No. Because it's that for bigger machines it requires performance, throughput, high performance. But Zephyr is not. Because for that scenario, for complex machines, we.
Why is that possible? Why it's not good?
Because it's simple.
Yeah, not simple. Then simple is better.
Yeah, simple is better. But when you have, of course you can use it, no problem. For example, in some, domain controller or central controller. Yeah. So, but. Yeah, it's not complicated. Yeah. So for that scenario, the performance, the cost is more than. Yeah, that's right. Stability, no problem. Yeah. But. Yeah. Yeah, that's right. So. Yeah. So it can guarantee the latency of time, but it cannot guarantee the performance, right? Because for big machines, people more require, high performance, high through output, right? So this is done very well, with Linux plus KVM. Yeah. Yeah, that's good.
All right, everyone. Welcome to our topic. I'm very excited to be here in the FOSSASIA Summit, sharing our topic, Introduction to openEuler Embedded and its Innovative Features. My name is Yongmao. Now I am the committer of the openEuler MCS repository, responsible for developing the Mika framework and auditing codes for developers when they upload their codes to our repository. Okay, in the following half an hour, I would like to introduce two main topics. The first one is Introduction to openEuler Embedded, including its key features, its general architectures, and its application scenarios. Then I would like to introduce the Mixed Criticality System Framework and its management framework for supporting multi-OS running on a single embedded OS platform. Okay, so firstly, thanks to Dr. Xiong's presentation about openEuler, now we may have a better understanding of what openEuler is. As we know, openEuler covers 4 main scenarios, that is server, cloud, edge, and embedded. And openEuler embedded focuses on providing competitive operating system technology for hardware resource-limited hardware platform. And because of the need to build customized OS, we choose Yocto as our composing system. So it's an open source project from Linux Foundation, and it's provided an easy way to tailor our operating system. Okay, so after knowing the relationship between openEuler embedded and openEuler, now I would like to provide a definition of what it really is. So we define it as an open and comprehensive embedded software platform. So it's not just the embedded Linux, but it's like a solar system. The sum is the embedded Linux. It provides the unified build, rich features, ecosystems, and standardized interface. And we also have some non-Linux planets which provide rich features, like T can provide security, RTOS can provide hard real-time, and bare metal can provide extreme performance, while the embedded virtualization can provide isolation and resource management. Okay, so let's take a deeper look to openEuler embedded. So the blue part are the scope of openEuler embedded. So for the hardware, we can support more diversified hardware than the cloud and server scenario. And for the application, we mainly support operational technology applications. And we would like to attract users and vendors to build your own application based on openEuler embedded to provide more interesting features. And at the bottom part, we have the Fusion Dock, which is a collection of technologies to support multi-OS running, so including virtualizations, containers, etc. And above that, we have the Mika framework, which is the management framework for lifecycle management for multi-OS. And we can also provide a communication framework for different OS communication. And above the Mika framework, we have various types of OS. For Linux kernel, we have configuration and optimization for different scenarios. And above Linux, we have many different kinds of interesting features. And the RTOS, we don't have a best for all option for it. So we supported different kinds of RTOS. So firstly, the Uniproton, which is a very interesting RTOS, also from openEuler community. And we have Zephyr, which is a well-known operating system worldwide, and RT-Thread, and very popular RTOS in China. And also, reliability is our focus. So we would like to provide the performance tuning, debugging, and chasing methods. For example, the Mika framework provide debugging methods for RTOS who has realized the GDB stop. And also, the tools and infrastructure are also very important because they are the backbone of our system and they are supporting our daily work. Okay, so let's move down a little bit to see the key features of our system. We have 1+x+1 feature. The first two features are the invariants, which is the two legs to support our operating system. That is the embedded Linux and the infrastructure, with the X features in the middle. And for the embedded Linux, we have high quality maintained kernel, which is the same kernel as other kinds of distributions of openEuler. And above that, we will do specific optimizations and configurations. Like we will apply prim-RT patch for soft real-time applications, and we will do fine-grained configurations and tuning to reduce binary size and memory consumption. As for the infrastructure, we choose Compass AI as the foundation technologies for our CI/CD system, and we choose Yocto as our building framework, as I said before. And we store all of our codes in Git, which is something like GitHub, but a more popular one in China. In the middle, we have the DSoft bus, which is a kind of a collection of technologies to manage and connect different node devices in a local network. And we have our mixed criticality system. So it provides the foundation technologies like hypervisors and containers, and we provide a management framework above it. And we also support embedded robot runtime, like we integrate ROS2 into our system. And we also have the embedded, we also want to provide more support for embedded edge and embedded AI in the future. So like we will integrate Cube Edge K3S into our system so that in the future, we will improve the collaboration between the cloud, edge, and embedded. And also we will integrate mainstream AI framework in the future, like the TensorFlow, PyTorch, or Mindspoor. Okay, so after knowing the key features, now you may be wondering like, so what does it look like when the openEuler embedded is running? So actually we have 4 running modes. The first one is the very typical mode. So that is we only run one Linux based on the embedded system. So now we can, get the advantage of Linux ecosystems, but the cons are very obvious. There's no guarantee of hardware real-time or high reliability, which are the advantage of RTOS. As a result, in the following 3 modes, we can run more than one OS based on a single embedded platform. For the AMP mode or the asymmetric multiprocessing mode, we deploy openEuler embedded and RTOS based on different types of CPUs. Like for example, we deploy openEuler embedded on A-tier ARM core cluster, and we deploy RTOS on M-tier ARM core. And the hardware resource is static allocated. So the disadvantage is the number of OS is limited by the hardware resources. Like if we only have 4 CPUs in the embedded system, then we cannot run 5 OS based on it. To resolve this problem, we introduce the virtualization mode, which can, which use the virtualization technology to provide, in theory, unlimited operating system to, provide the chance to run unlimited operating system based on a resource-limited hardware platform. However, because we have poor support for heterogeneous cores, so hypervisor can only run on homogeneous cores cluster. As a result, in the end, we have diffusion mode. So we will run AMP mode for heterogeneous cores, and we will run virtualization mode for homogeneous cores. All right. So actually, we can deploy our operating system as 3 different kinds of system. So firstly, we can deploy it as a server so that it can control different kinds of node devices through internet. And we can also deploy it as an edge-based system for edge computing. And we can also deploy it as just, as it originally designed for the embedded system. And it can control different kinds of peripherals. Okay, so I want to make a small summary for our ecosystem. openEuler Embedded is an open and comprehensive software platform. It includes the embedded Linux part, which gains the kernel from openEuler community, the same kernel as the other kind of distribution. And we use Yocto as our business system, which is different from other distribution. And we also have some non-Linux parts like RTOS and hypervisor. For the applications, we support industrial IoT, robotics applications, energy industries, and BMC, which stands for Baseboard Management Controller. And we have some applications for it. Like we have applied our operating system into the industry controller, the unmanned vehicles, and some interesting robots. Like last year in the openEuler Summit, there is a very interesting robot. If you stand in front of the camera, the painting robot can paint a picture for you. So it's also run the openEuler embedded inside it. All right, so I would like to introduce the development board. So EulerPi is a series of development boards designed for running openEuler embedded. And High EulerPi is one of it. And its SoC is SD3403, designed by High Silicon. So we name it High EulerPi. It has very powerful hardware and can run complex software based on it. And its usage is mainly for industrial control and robotic applications. It can support various types of communication protocols and peripherals. Okay, so secondly, I would like to introduce our mixed criticality system framework. So at first, I would like to make a small metaphor to help you understand what is mixed criticality system. So in the past, like we only have small flower pots. In each flower pot, we can only plant one single type of flower with very limited quantity. But with the time flies, we have more mature pot making technologies. And nowadays, we have very big flower pots. In each flower pot, we can plant various types of flowers. And also, each type of flower are isolated. For example, if one bunch of flower dies, it will not affect other bunch of flowers. Okay, let's move back to the field of computer science. In the past, we only have very simple hardwares like the tiny MCU. So we can only run something like bare metal applications or small RTOS based on it. And nowadays, we have very complicated SoCs with multi-cores, even heterogeneous cores, so that we can run more than one OS based on the SoC. So like we can run Linux plus RTOS plus other kind of bare metal applications. But to ensure the safety, we need to provide an isolation mechanism so that if one OS dies, it will not affect other OS running. Okay, so maybe now you have a general understanding of what MCS is. So now I would like to provide a more clear, more strict definition. So as its name says, MCS stands for Mixed Criticality System. So literally, it just stands for a system with mixed criticality components. So what does criticality stands for? It mainly refers to safety, but it can also extend to other notions like real-time, security powers, etc. And we mainly focus on three parts of MCS, that is the deployment, quarantine, and scheduling. So firstly, we need to deploy different kinds of OS onto the platform so that we now have the mixed criticality. But that is not enough because to ensure safety, we need to provide quarantine between different OS. And then to achieve a better overall performance, we need to implement scheduling so that like the virtualization, if one OS is in idle state, it can allocate resource for other kinds of OS to achieve a better overall performance. And we believe it's the future trend of embedded systems because of two reasons. From the server side, the hardware is evolving from distributed one to centralized one. Like for example, the ECU in automotive vehicles, they can only do very simple tasks. But nowadays, they are evolving into a zone controller to control a large area of hardwares. So we need a more complex software to do the control. And from the client side, we are having more and more complex node devices like the drones nowadays. They should keep balance at the same time while taking photos and transmit the data back to the cloud. They are doing many complex things in the same time. So we may need, more than one OS for the different applications. All right. So I would like to introduce our mixed criticality deployment framework. Why we call it deployment framework is because for the quarantine and scheduling mechanism, they are implemented by the foundation technologies like virtualizations and containers, which is included in the Fusion doc part. And our Mika framework mainly focus on 4 parts. That is the lifecycle management, cross-OS communication, service framework, and multi-OS build infrastructure. So for the lifecycle management, we provide a unified interface for multi-OS management so that we can hide the differences of the foundation technologies in Fusion doc. As for the cross-OS communication, we provide a shared memory-based and lockless framework to support efficient communication. As for the service framework, we define the service interface as different OS provide different services. And in the end, we also provide a unified resource description so that different OS can dock into our Mika framework more easily in a more standard way. Okay, so we can take a deeper look into our framework. So for the lifecycle management framework, actually because it needs to control the hardware. So actually it's an platform independent framework. We will take RMVA architecture as an example. So firstly, if the Mika framework want to put up the remote processor, it will send an SMC call to the bottom level firmware, and the bottom level firmware will do the actual work to boot up the CPU of the remote operating system. And for our framework, we mainly use the remote proc framework as our base technology for doing most part of the lifecycle management. So remote proc framework is a framework in Linux kernel, and it provides the a standard way to abstract the remote operating systems. Like in the framework, the remote operating system, each the remote operating system is a remote proc instance. So in our Mika framework, we have many remote proc instance. And below the remote proc instance, we have a unified resource manager to manage all kinds of resources in our Mika framework. And above each remote proc instance, we will call the interfaces of remote proc to load our OS binary to the destination memory and parse the resource table and boot up, etc. Doing a lot of things. And for the resource table, so it's a very interesting and very special data structure in ERF format. Each entry of the resource table indicates a type of resource for between the two OS, as there is a shared resource. Okay, as for our service framework, for now, we mainly depend on the RP message framework from kernel as well. And if we have one service between the two OS, then it will establish one specific endpoint for it. But for the abstraction, the service is another kind of abstraction other than the endpoint. So it's a more abstract notion. For example, we can have pseudo terminal service, that is the PTY service. But for the two OS, they may have more than one PTY connection. As a result, for a single service, we may have more than one endpoint, mapped to it. And also, we can provide self-defined service like the debugging for RTOS with GDB stub. And the bottom level is not implemented with RP message framework. We are implemented with our own defined data structure. All right. So then I would like to introduce the history and the future of the Mika framework. So in the past, we only implement the OpenAMP-based Mika framework so that we can only support many deployment, but poor quarantine and scheduling. And now we are developing with many, excellent virtualization technologies like the VMs, like Rust ciphers, and we also want to use the lightweight containers to, to enrich our ecosystem. And as a result, in the future, we want to support both heterogeneous and both heterogeneous and homogeneous cores, and support even, the collaboration between the node device and the cloud systems. Okay, so I would like to show our envision of the future framework. So firstly, we will deploy many OS based on the, the homogeneous core cluster with a type 1 hypervisor. Because it's the type 1 hypervisor, even though different virtual machines are isolated, they actually have a management VM for management the whole hypervisor system. Sorry, the virtualization system. And because the management VM is responsible for take control of the communication in and out the system. So like if the two VMs want to send interrupts to each other, they need to pass through the management VM. But to improve the efficiency of data transmitting, the two VM can directly establishing their data transmission channel. And secondly, we can also deploy our operating system to heterogeneous cores. And the communication can happen in the physical memory. Of the physical layer, we have the VirtIO protocol as the link layer protocol. And above that, except for RP message protocol, which is a kind of transport layer protocol, we also want to support other protocols like UDP and TCP. And above that, we also want to establish our own RPC framework, that is the remote procedure call framework. And thirdly, we also want to modify the exhilarating so that exhilarating is a kind of lightweight container technology, which is something like Docker, but it's from the openEuler community. And we want to modify exhilarating so that users can deploy operating system through K3s, through exhilarating to the Mika framework to here or here to the embedded device. All right. So at last, welcome to engage in our openEuler community, and these are the resources for you. Okay, thank you for listening. If you have any questions, welcome to ask. Please.
How is the quarantine aspect of MCA and Mika enforced when you've got operating systems on the same hardware?
So you are the quarantine technologies for our Mika framework? So we mainly implement it through the virtualization technologies or container technologies. So we will not implement it by ourselves because there are some mature technologies for it. Yeah. Okay, thank you.
What are you using for a BMC? Are you using OpenBMC or an existing project?
Actually, we, community members, they are implement our system, but they're not OpenBMC image. They are using their own company-developed BMC applications. However, our community has implemented the OpenBMC image, so you can have a try. Yeah. Yeah. So anyone else? Oh, okay. So another thing to mention, Dr. Ren is our chief architect of openEuler Embedded, and if you have more questions, and you are welcome to ask him as well. Okay, thank you.
From China. It's my first time to come to Vietnam. I'm very excited and honored. Yeah, so many young faces. My topic is accelerator framework, UADK. I worked for Linaro for over 10 years and have been collaborating with HiSilicon for over 10 years. Now I'm maintaining the kernel submodule UACCE and also maintaining areas of UADK like the openSSL and DBDK. We are also upstreaming the SBDK UADK component. Here is the agenda. First, the overview and some components of the UADK, and lastly, the performance. As we know, there are many accelerators like GPU, NPU, TPU, and also more and more user drivers like DBDK, SBDK. Also, we want to the better performance like zero copy. We cannot want to memory copy from user space to kernel space. So it's better to directly have provided the user driver. And lastly, the security. We all know the kernel is safe. We can trust the kernel. But if the driver is in user space, can we trust it? This is our UADK overview. UADK is based on the IOMMU. So it provides boundary check and the permission check. For example, if your driver cannot access other area of the accelerator, you can only touch your own accelerator. So it is much safer. And our MMU provides SVA feature. That means shared virtual address. So in the user space, we can directly use the virtual address. And for it is a user space driver. In the user space, we can directly do the DMA to the accelerator. What's more, with SVA feature, we all know usually we have to use physical address, but with SVA feature, we can use virtual address directly. So it is very convenient. Thanks for the pass ID. We can do using multi-process because the pass ID can distinguish them. Then it contains several modules, the kernel module and the user space module. This is a general framework. In the bottom is accelerator. It can provide several queues. Each queue can provide a service. So many queues can work simultaneously. Now how user space use that queue? So the accelerator have to register to the UACCE. With the help of UACCE, then the application, multi-application, can directly open the UACCE to get the access of the queue. For example, the left is pass ID 1, is application 1. The right is pass ID 2, is application 2. So they can run in the meantime. The pass ID can distinguish them. Also, in the in the pass application one, we want to access 2 queues or many queues for the multi-thread for the better performance. So you can open multi times. The USC can use our MMU for the bind. So our MMU can bind the device to the current MM. The code is already merged in the kernel, in the 5.7. Is there here any question about this picture? This is a general framework of the USCE. Okay, next. This is SVA, general SVA. We all know the MMU. CPU has MMU. It has a patch table. So the application uses virtual address. Also, device also has MMU. It's called SMMU or our MMU. It also has a patch table. So there are 2 patch tables. If so, why not the same? So now the SVA feature use the same patch table. The MMU and SMU, they share the one patch table, only one patch table. So they can know each other. With this, the DMA can directly use a virtual address. And also their page fault, our page fault, similar like the MMU. For example, in the SMU3, when their page fault happen, the handler to call the handle MM fault. It is same as the MMU. Then it will provide the memory for you. Is that okay? This is how accelerator use the USCE. In the accelerator driver, in the pro process, it has to unlock USCE and then register to the USCE. The USCE was using the RMMU feature to open the RPF feature and SVA feature. And after that, it will provide a chart device. So with that chart device, the user application can access to the accelerator. In the remove, the USD will do the USD remove. Also, it provides some ops when the register, like get queue, put queue, start queue, stop queue, and memory up. Then, so after the registration, the application can directly open the USDE. It is a chart device, so it simply open the chart device. With that open, the USD will bind the device, the accelerator, with the current MM. So after that bind, the virtual address can be directly recognized for the application and the accelerator. And the USD will get a queue from the accelerator. And after you open, after the application will map the MMRO is doorbell. Just prepare DMA and send doorbell to tell the accelerator to start the DMA. Also, map the other area for the DMA ranging. And then you can all control to start. After the preparation, you just prepare the DMA, prepare the data, and send a doorbell to tell the accelerator to start. After that, you can just pull. You can pull the FFD, or just keep reading. And all the finished, you can put Q, and close FD for the last time. This is the user application to use USDE. That's the kernel module USDE. This is the whole picture of the UADK. The right is a picture. In the bottom is accelerator. Then the kernel space, there are kernel driver USDE. After then the user space, there is the library is a UADK library. We can provide the user driver. Currently we but be careful. There are two requirements. Firstly, the our MMU have to provide the SVA feature. Also, the device have to support because the pass ID. We can use the accelerator in the multi-process. So the device has to recognize the pass ID. If the accelerator does not support SVA, you cannot use it. In the high silicon platform, currently we use crypto. Like crypto accelerator can support this feature. We provide compression like zip, gzip, deflate, and ZSTD. Also, the asynchronous crypto, like ICDH, ECC. We know the async crypto is very costing. It needs a long time because it is not like the CMYK crypto. It's very simple and much faster. So I think like ICDH is very if you do it using the CPU, it needs a long time. So it's very suitable for the crypto, for the accelerator. We provide the ICDH and ECC. Also the digest is just like a hash, MD5, SM3, etc. Now we support our UADK to the DBDK, also the SBDK. You can directly use it. Oh, sorry. This is the performance. The green line is using CPU. The brown color is hardware. We can simply see. For example, the first line SM4. If using the software and the hardware about 4 times better. Also, the CPU rate is much downgraded. And the zlib and the gzip also almost 20 times better. The IC is also 3 times better. This is performance data. We test this on the high silicon Qualcomm 920 platform. This is a host. This is a guest. In the guest, there is we have to use the virtual RMMU. It needs the lasting translation. It is still in upstream. We use techniques to support the better performance in the guest. We know in the guest there is some penalty because there is a nasty translation from the virtual address in the guest have to translate to the physical address of the guest, and then lastly the physical address of the host. So there is some penalty. We just use some technique. Use a huge page. Use 2 megabytes huge page is used to decrease the TLB miss. With this technique, the performance in the guest almost comparable to the host, about 85% or 90% of the comparable to the host. This is the guest. This is the UADK test for the openSSL. The blue line is soft. The yellow line is using hardware accelerator UADK. You can see the sign, for example, the left sign is much better, 4 times. The verify is a little bit better. And SM3, for the big data, because hardware usually do better in the big data, big packet size. We have to prepare, and if using small size, the CPU is better because there is no preparation. SM4 is also the same. Using the big data is better. Here is DBDK. DBDK was also supported. It already merged in 22.11. We are now upstreaming for the SBDK. So in the SBDK and the DBDK, we can directly use the UADK components. We can see also the same. The small packet, the software is better because there is no preparation. You can use anytime with the CPU. But for the big packet, the bigger the better. Hardware is better. You just prepare data to the accelerator, and then you don't care. Also, since the UADK it provides the crypto and the compression, so now the UADK only have, if you use UADK, you have to have the accelerator. But sometimes you may not have the accelerator. So we are investigating using the CPU structure, CPU instruction. We tested this is tested with Neon CPU instruction. You can see the instruction is also better than the software. The software is not a CPU instruction, just a CPU. You can see it's also better. So the total solution of the UADK, we also added the CPU instruction, like the CE. We are CESV. CE means crypto extension. SME means scalable vector extension. They are ARM-V8 feature. So if you have ARM-V8 CPU, you can use these two CPU instructions. So we also adding these two instructions to our UADK solution. We are just adding this. See the blue line. Also, the openEuler ACC lib, we have meetings bi-weekly. If you have interested, you can join this meeting. That is GitHub. This is the simple description of Ninaro. We come from Ninaro, and Ninaro has many maintainers. We have we always the top 3 contributor of Linux kernel since over 10 years, since 2011. So we have many. Also, we provide some like a special feature like TE security. TE is still developed and maintained by the Ninaro. So if you have interest, especially on the ARM ecosystem, you can contact with us. Yeah, that's all. Thank you. Any question? Okay, thank you.
All right. So I guess we'll start. Hi everyone. You are in the vector processing with the RISC-V vector extension talk. So I'm Rémi Denis, and I happen to be, well, you don't really care, but I happen to be a software security research engineer. And this is not, I'm not talking about my work today. I also happen, and that's closer to this presentation, I also happen to be one of the main developers for the VLC media player, for those who know, sorry. And I have about 30 years experience in this industry. First, let's talk to optimize programs, calculations. So when I started computing, I was still a kid and I was using my mother's computer. And back then, not working very well. It was running at 0.008 gigahertz. So it was pretty slow. But back then, it was nice how to make your program faster. You just waited a few years, got a new computer, and it was just faster. And in 2003, I got my first own computer at university, and it ran at 2.8, so several hundred of times faster in just 10 years. But then something happened. We got close to the physical limits, and we couldn't increase clock frequency anymore, but instead we increased cores. So how to speed up the program? Well, obviously, first we tried increasing clock frequency. Then we used multiple threads, so there's symmetric multiprocessing and symmetric multithreading, which are kind of similar tech. The problem with those is you need to make your program multi-threaded, and that's notoriously difficult and doesn't always work even. Or you can use specialized processing units like GPU, NPU, VPU, ISP, and so on. And there's another trick that has been also used for general purpose computing is to use superscalar execution. And superscalar execution, is, well, you make your processor do multiple things at the same time in a single thread. And for instance, let's say that I want to calculate the sum and the difference of two values at the same time, so A0 and A1. Well, I will have those two instructions to run on the processor. They're independent instructions. I can run them if the processor is able to run them in parallel and save a lot of time by doing this without increasing the clock frequency. Of course, you need to increase the processor size. Now, the problem with this, you need to decode multiple instructions, and you have to look for dependency hazards or data hazards between the instructions, because, for instance, if you want to sum A0, A1, and A2, well, the second instruction depends on the first one. I can't run them in parallel, because if I would do that, then it would, obviously the calculations would be incorrect, because I need the result T0 of the first one to calculate the second one. So here comes vector processing, or sometimes also called SIMD or SIMD, for single instruction, multiple data. The idea is to apply the same instruction on multiple data elements at once. It's also called vector because, well, it's kind of like, you can think of it kind of like linear algebra if you've done first cycle math. And here, this was popularized in the 90s by Pentium MMX. And we basically tell the processor explicitly that we want to execute multiple calculations in parallel, and that it is safe to do so. Of course, it means we take the responsibility as a programmer to guarantee this to the processor to enable faster speeds. So today we're talking about this on RISC-V. So RISC-V, as many of you probably already know, means is a new instruction set architecture, which is an open standard with, in principle, royalty-free and no patent encumberment. And it means reduced instruction set computer, which means that it's very easy to decode instructions for the processor. You don't waste. So your processor, you can dedicate it to calculating things and not to wasting time decoding the instructions, which would be the case on an Intel processor. And this also means that anyone can design their own processor. You don't need a patent license like for x86, or you don't need to buy a license expensively from ARM Limited, like on ARM. And you have vendors from China, US, Europe, and I don't know about Vietnam, but it might also be. So RVV, or RISC-V Vector Extension, is an open standard. There's already some open source designs for it, and there's also some real hardware. We'll come to that. It's also, the reason I'm talking about it is also it's a lot easier in 25 minutes to explain that than x86. And an interesting aspect compared to x86 especially is that it's scalable. So it basically write once, run anywhere. I think you've heard this story already in the stocks in this track today. So availability, there's currently one piece of hardware that's widely available, and it's actually quite cheap, so about 1.5 million dongs. But I think we are going to get, this is credit card size, we're going to get much better hardware within months or years. You can also emulate it on QEMU, of course. Just install the, on Linux, you can just install the binfmt QEMU wrapper, and it will literally run your RISC-V programs directly on your x86 or ARM Linux system. So this is really convenient for testing purpose. Anyway, that was the introduction. So let's have as simple as possible, still not that simple, but motivating example here. Obviously, in 25 minutes, we are not going to go through the 190 plus different instructions in the instruction set of the vector processing unit, but so the classic example for vector processing is sac function, which means sum of ax plus, well, calculate a times x plus y. And this, but if you know C, but even if you don't know C, is fairly easy. So what we do is we calculate the product of vector x, scalar value or constant value a, and then we add a vector y, and that gives us a vector. Obviously, this is a linear algebra. And this is a fairly simple example of how you can do vector processing, because we are actually doing vector calculations here. I'm going to rewrite that function a little bit in a way that is more like the computer would actually want it, or the compiler would optimize it for you. And this is just essentially just removing the iterator and instead directly incrementing the pointer addresses as we go. It's actually faster to do it like that. And in practice, your compiler would do it for you, but this helps to understand what happens. So essentially, at each iteration of this loop, we decrement the number of elements that we still have to process, and well, we have to increment the 3 pointer addresses that we have as we go down the vectors. So one element by one element. But obviously this element at a time, it's not very fast. So it in a way that is even more close to how the computer would actually see it, and we don't have while loops in computer. We only have conditional branches. So in practice, well, this is our main function. I've renamed the variables to use register names so that we can map it then to the code that's going to come on the next slide. So A3 is a count value. A0 is the first argument. It's target or output vector memory area. FA0 is a constant. It means floating argument number 0. A1 argument 1 is a second argument that is not a float, so it's the x pointer address here, and A2 is y, and then A3 is a counter. So this is what we would actually look like in more like pseudocode type of like how the compiler would probably implement this in practice. Of course, it's going to be in, with assembler instructions, but we'll get to that. And we, of course, have to have an explicit return at the end. So I don't know if many of you have done assembler before, but if you want to optimize down to the instruction level, that's how it gets. For RISC-V, it's actually fairly simple. So instead of, now we are switching to assembler. So we're going to have to write this at the top of our source file instead of a .c. So we just say that, okay, first is .option arc is a directive for the assembler, which says that we are enabling the vector extension. Essentially, we are telling the assembler that, okay, it's okay to use vector instructions because I know my processor will have vector support. And likewise, we enable the ZDA. It doesn't matter much. And then we say .text. This means we are now writing code, which is text or the story for the computer, if you will. You could also write .data, then it would be like constant data or modifiable data. But text means that it's a computer program. And then we say we have a global function or global symbol, which we call saxpy. And yes, there's no A here. It's how it is. It's not a typo in my slides. It's actually like that in the. And then we say, okay, saxpy function starts here, and then we'll write our code. So after that, well, how do we put this? So how do we put this in vector instructions? So if you have never seen assembler, this is going to look a little cryptic. Let's get through that step by step. So first we have to tell the processor what is the vector length. So the number of elements that we have in our vectors. In this case, this was a count variable, which is now the A3 register, if you recall the previous slide. So here we tell it, well, we have A3 elements, whatever values that happens to be, and each element is 32-bit because we have float, and float is single precision floating point values in this example, so it's 32-bit per element. We could put 64 or 16 or 8 depending on the data. So if you want to do AI, for instance, it's going to be half precision, you could put 16-bit. You could say E16 to have 16-bit floating point calculations, for instance. And then, well, what we have here is so A1 and A2, X and Y vectors, they are pointers or addresses in memory. So the data is in the memory, it's not in the processor. So we need to move that data, transfer that data, or copy that data from the memory, the RAM, into the processor where it can make calculations. And this is called loading. So we do V for vector, L for load, and then E32 means element of 32-bit. And we say we load that address A1, and we load it into, we need to put, so the processor has 32 vector registers, named V0 to V31, not very original. And we need to pick one, like, it doesn't really matter as long as we remember which one contains what. So here I took 0, and this will load what was at address A1 into vector register 0. And then we do the same for Y, so from A2 into V8. So now we have we have copied the data of X and Y into the processor. We need to multiply X by constant A. Constant A is a parameter, so it's already in the processor. We don't need to load it. So we can directly do a multiplication. So this is V for vector, F for floating point. If you don't put F, it would be integer. Mul for, well, multiplication, obviously. Dot, and then we say what we are doing, what data we have input. So VF means one vector and one floating point value, or one scalar value, or one single value, singular value, if you will. Here, for instance, the next one, you have VV. This means we are operating with two vectors. And here, VF means we have one vector and one scalar, or one singular value. So this calculates FA0 times V0 for each element in V0 and puts the results back into V0. So in assembler, usually you have the result on the second parameter, the first parameter. And then we do the add. So V8 plus V0 also into V0. This will add, well, this, which is X times A, with V8, which is Y. So we have our result. But now the result is in the processor, and we need to transfer it back into the memory, which, of course, where the calling code or the program expects it to be. So we need to do the opposite of a load, and the opposite of a load is a store. So vector S for store, E32, because again, we have 32-bit elements, vector, and we say we are transferring the content of vector 0 into the address, the memory location or pointer A0. It's kind of looks like this in C or in Rust or in like C++. All right, but there's a problem. So if we do this, the processor doesn't have infinite capacity to store infinitely large vectors. So if you have like 1 million vector and 1 million element in our vector, 1 million dimension vector linear algebra, this is just not going to work. So there's a trick here is that this T0 here, it will contain the number of elements that the processor is able to process at a time. And I mean, it's going to be more than one, but it's not going to be absolutely huge. But we are going to have to iterate this set of instructions several times, and every time we will operate on T0 elements until we are down to until everything is calculated and we can exit the function. So in total, okay, it gets a little bit more compact here. So we again have a set vector length, then we count down. So A3 is the counter, so we just subtract. So we are going to process T0 element, so we can subtract T0 from A3 and update A3 and this. And here at the end, we check if A3 is not equal to 0, then we go back to 1. Then we have our load. So this is X, this is Y, this is the multiplication, this is the add, and this is the store. And here we have so this SH2 adds are just updating the pointers, so incrementing the pointers across loops. So the way this works is that, actually I think there might be, it might be A1, T0, A1, but this adds, so SH2 means shifted by 2 bits to the left. So this is shift a value by 2 bits to the left, multiply by 4 in other words, and then add it. So this calculates A1 equals A1, well, this updates to add 4 times 4. And the reason why we do T0 times 4 is that we have 32-bit elements or 4 bytes elements. And in C, the compiler will do this adjustment, this multiplication for you, but in assembler, the pointers are always in byte values, so you have to adjust for the size of the elements you're operating with. Because if you think about how a pointer actually is represented in memory, if you've ever printed a pointer like in hexadecimal or something, you'll see that it's always in byte value. So we have to manually multiply by 4 because our elements are 4 bytes. Of course, if we had 2 bytes element, because we would be doing AI stuff, then it would be times 2, and this would be SH1, because to multiply by 2, you have to shift by 1 bit to the left. And that's it. So at the end, we check if A3 is now down to 0, and if it is not equal to 0, then we go 1 to label 1. B means backward, so back up. We could put F for forward, but today, of course, it's backward. So yes, so that was the main hard part. Now we can rest our brain a little bit. And I mean, I know it's a little bit complicated. When it's around, it's actually much more complicated on other architectures. So let's go back to this set vector length instruction. So as I said, we have element size, 32-bit in this example. A3 is an input. It's telling we have this many elements available that I want to make my calculations with, and T0 is the output. Number of the processor tells us, the programmer, or conceptually, how many elements it can process in one iteration. And on current hardware, which I mentioned earlier, in practice, we have 128-bit vectors, so 32-bit elements in another 28-bit vector, we're going to get 4. I mean, of course, assuming that A3 is larger than 4, then we're going to get T0 is going to be equal to 4, which means we get a speed up of 2 to 4x times approximately. Of course, it depends on the hardware, but we can do better than this. And I mean, this is significant, but if you have a large scale, if you pay per minute of your VM runtime on some cloud service, increasing your performance by 4 times is actually a huge cost saving, but we can do much better than this. So there are additional parameters we can add here. M8, TA, MA. And M8 is officially called the group multiplier, but it's essentially an unroll factor, which I explained what it means. It's basically saying that, hey, if we go back to, you can, I have a URL to the slide, you don't need to go take photos. Yeah, so if we go back to this, I'm only using V8 and V0 here, and I have 32 registers. I'm only using 2 out of them. That's kind of not very efficient use of my hardware here. So I'm like, well, I only need 2 vectors for this calculation. So how about I'll just pretend that I have fewer, bigger vectors. And the maximum you can use is 8. And so what this means is that essentially V0 becomes a representation of all vectors from V0 to V7, so V1, 2, 3, 4, 5, 6, 7. V8 becomes 8, 9 to 15, and if we would use 16, it would be all the way to 33, and then 24 to 31. So by doing this, we end up having only 4 vectors, but they are 8 times larger than they would be if we had just used a normal M1. And this, again, improves the performance quite a bit. Like with this, we would typically get like 5x to 8x maybe. Yes, of course, it doesn't scale infinitely, but, and I mean, of course, we can use other values. So if we need more vectors, we have M4, M2, M1 is the default, and we can even go into fractional, so half, quarter, and eighth. TA means tail agnostic. It basically means that if we have less than 4 elements, if we have less than the maximum, we don't care what happens to the stuff after the end. So that's why it's called tail agnostic. The tail is the stuff. So if say you have a vector of 4 elements, capacity in your processor, and you have only 3 elements that you actually want to calculate with, you're saying that the 4th element at the end of the vector, I don't care what the CPU can do. It does with it. It can do calculations. It can ignore it, whatever. So essentially, you're telling the processor, please do whatever is fastest. For your implementation, I don't really care. And similarly, MA is mask agnostic mode. This is about masking. I'm not going to go into the detail of masking. If you're interested, you can read the specification. But again, it's another way of saying that don't need to worry about masking in this calculation. You can do whatever you want, whatever is fastest. So this, and that's pretty much it. So, and we're on time. References, well, obviously I only add, so we only have like 5 instructions. In reality, vector instruction set is about 190, give or take, different instructions. I mean, you have subtraction, division, well, you don't have division, but you have all sorts of integer addition, like XOR and OR and 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 add and sub and reverse sub and whatever, and even more complex things like min, like which A plus B divided by 2. So I can't go through all of them. If you're, of course, in real case, if you want to take this into use, you're going to have to go through the RISC-V vector extension specification, which has all the list of all the instructions, and they are nicely grouped into different families, like integer, float, mixed with, and all sorts of things. The unprivileged ISA specification is a baseline RISC-V instruction set for like doing the base things like sub and branching, for instance. Again, I mean, you might need another condition, branch condition here. This is just an example. You can go to the unprivileged ISA specification for that. What's nice to note is that they have separate specifications for unprivileged and privileged. And if you're just writing like software, normal software, you can just use the unprivileged. Privilege is if you want to write kernel code or hypervisor code, which does the memory management, that sort of thing. So if you do, here we don't care about that. So we have half of the specification that we don't need to care about. And then you have the ABI spec. That's where it tells you, that's a spec that tells you like which, how to like where your parameter and your return values are going into the which register or where they are going, and how the data is laid out in your memory. It's essentially mapping the C and C++ and Rust and other D and all these native compiled language, how they map to the processor on this specific architecture. And you have ABI specifications on every architecture. There's an ARM ABI, there's even ARM 64-bit ABI, 32-bit ABI, x86, so there's a RISC-V ABI. And you can find all of these on the RISC-V GitHub. The slides are there, so if you need to take one screenshot, if you need to take one photo, it's this one. And also full working sources with the makefile and stuff there, and that's it. Yes? So in my experience, obviously it depends a lot on the implementation, and because RISC-V is an open specification and not a hardware as such, it will depend on the vendor. So this hardware I have, which is currently the main available hardware coming from, well, it's Canaan, but it's really made by T-Head, which is a subsidiary of Alibaba. I think for this loop, it gives us between, well, maybe 6 to 8 times faster, but it depends on the loop. And compared to x86 or ARMs, I think compared to ARM, it's roughly the same, typically. Of course, it depends what processor you have. Usually, you can't choose. Yeah, so x86 is AMD and Intel. So for x86, it's a bit different because x86 usually, on the face of it, using MMX, well, not MMX, but SSE or AVX will give you better improvements than this. But the reason I think is more like on Intel, the CPU is really slow for like non-vector calculations, for scalar calculations, because of the complexity. Because of the complex instruction set, they have to do a lot of work in decoding and like pipeline, like speculative execution, all sorts of things. And because of this, the scalar execution mode is actually quite slow. And because of this, they get a lot more benefit from vector calculations than a simpler RISC architecture like ARM or RISC-V. And for this reason, I think this is one of the reasons why you will see that AVX is actually giving you better performance compared to like plain x86 than RISC-V vectors would give you compared to RISC-V, and also if you compare like ARM Neon or ARM SVE to plain ARM. Yes.
You mentioned the E series RISC-V. So even the hardware is just use a better hardware from this year. It's just the hardware from your company or the.
So I don't make hardware. I'm a software engineer. I mean, I think this year several vendors have announced that they will release hardware, but the problem when they announce is you never know, did they make sense and then make hardware with, which then means that you have 1 or 2 years to wait before the CPU comes, or does that mean that they actually have a board that's coming, like that you can buy and order on immediately? So currently this one is available. It has been available since October last year. And if you order it today, you'll get it in a week. But there will be better hardware from a variety of companies. So you have T-Head, Alibaba in China, and also Star5. In US, you have Sci5 and Tentorrent, I think. And well, there's a whole bunch of them. Because it's an open ecosystem, there's a lot of competition. So the vector specification version 1.0 was released 2.5 years ago. Yeah, approximately. They're not touching the base spec. They're adding encryption extensions to improve the speed of also encryption algorithms, and maybe some stuff for AI. I don't actually know what they're adding. Yes? How many or what? So this hardware there, it has one vector capable core and one non-vector capable core. So it has 2 cores, only one of which have vector support. But again, there are some boards already available with 4 cores or 8 cores, and somebody has even made like a super calculator with like I think 1,000 cores. RISC-V is just an instruction set, so you can do designs of whatever you want. I don't think there's a fundamental difference between, in terms of how many cores you can make. It doesn't really matter which instruction set you have. You can make them really large. You can make them really small. RISC-V scales up and down. And as I said, like of course, if you have multiple sockets, you could have really a lot of CPU and once there is one such hardware. I don't remember the Milk-V something. Some Chinese company has made some really hardware with a really lot of cores, but they don't have this yet. So it's gonna take a few more years to get high performance vector cores, I think. So currently, obviously at that price, you're not gonna get a supercalculator. So this is good for early testing and benchmarking, but I think in a matter of year or two, we're gonna get really performant, like more like server class or mobile phone class type of cores coming. But I mean, I'm not a vendor, so I can't really. And if that's all, then I guess I'll release everyone for lunch. All right.